Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 48 today and we are discussing about the classical peel test. So in the last lecture I presented about the peel experiments and how to estimate the fracture energy from the peel force. I also explained to you that the peel angle needs to be considered, the peeling rate needs to be considered. So, the peeling rate we will not talk much about, but then there is another aspect which also we neglected is the contact line. The contact line in the case of this peel experiment, peel test, we consider to be assumed to be smooth and straight, but it is not so. The contact line has got some undulations. So, we will like to discuss about that aspect, and after that I will like to talk about the bending of this thin plate, because when you peel it there is a bending of both the adhesive and the backing of this adhesive tape. So, that bending also needs to be considered and we will talk about that as well. So, this is what we derived in the last lecture. G is equal to P by W into 1 minus cos theta. So, the theta is the peel angle, but we considered that the peel front, this front remains smooth. So, we did not worry about it, but actually what happens is there is some undulations, and then if you notice these undulations, they appear to have a constant wavelength. Okay. So, lambda. So, how this lambda depends upon the materials, let us say it is a softer adhesive or harder adhesive, or let us say a softer substrate backing or a harder backing, and so on and so forth. So, there are many such questions and we will like to present some qualitative. I am not going to any quantitative or mathematical modeling of this phenomena, but some experimental observations I will like to present to you. So, this is what it is, but before that, this peel experiment we have shown in this in the rectangular geometry, but it can also be done in a circular geometry by what is known as this kind of blister test. So, basically this is this thin sheet, okay, and then it is remains bonded to this substrate, circular disc actually, with a hole at the center, and now this bonding is over here, the good bonding, and now that you apply the some liquid or air, you press it, and as a result this opens up from this front in a circular geometry. So, people, depending on the experiment or depending on the practical situation, one wants to find out this blister test, one has to do this blister test as well. So, there are papers in that, research articles, you can have a look at it. I am not going to discuss that in this lecture. I will now go into this instability or the contact line undulations that happens. So, what I am going to present is essentially from my own research. So, here and that we investigated to find out this contact line instability that happens in most scotch tape. So, what we have done is in a very controlled experiment, and that is what I would like to present to you. So, in a sense we have this rigid substrate, okay, and on this rigid substrate we have this elastic adhesive film which is bonded to it, and then from the top of that on the top we bring a flexible contacting plate. This is a flexible glass cover slip, and we have surface, on the surface of the cover slip we have got a monomolecular layer which is called a self-assembling monolayer, of a molecule that leads to only dispersive interaction, that is only dispersive interaction, no hydrogen bonding or other kind of interaction, dispersive interaction. So, this plate is brought in contact to this particular adhesive film, and then we give a small lift from one end. So, this end it remains completely in contact. Over here it is a spacer that is used. So, what happens is that when you place this glass plate like that, the contact line moves from this front towards the left and eventually comes to an equilibrium position. So, this is x is measured from this contact line over here. So, this is the distance a, that is the distance of this contact line from this spacer, and spacer height is delta here. So, this is a perfectly elastic incompressible film, and with shear modulus we can vary. We can this particular cover plate we vary also the flexural rigidity we call it. So, what is that particular term? I come to it in the next lecture or so. So, or in this lecture later on about this flexural rigidity. So, we basically we vary the thickness of this plate, and we actually go for a very low angle of peeling, in the sense that we have a, let us say the thickness of this plate is, let us say about 150 to 200 micron thickness of this plate, and then this, whereas the delta, this is maybe about, let us say 200 to 300 micron or like that, 200 to 300 micron. So, in a sense this is a very low angle of peeling, and that happens because this cover plate, this flexible plate is somewhat is somewhat stiff, more stiffer in comparison with most adhesive tapes. Okay. So, we have done it by design to make to satisfy the condition of very small bending approximations. So, we want to do the experiments at a very small bending approximation. Okay. That is why we have kept this this peel angle. I mean, if you measure the peel angle, it will come out to be a degree or so. Theta will be 1 to 2 degrees, not more than that. So, this is the experiment that is done. You can have a look at my paper. This is PRL 2000, in which we describe this experiment. So, this silent monolayer that I was saying, self assembled monolayer to make it only dispersive interaction. So, I have already discussed about that. So, when you do this experiment, we see at the contact line, this contact line, very beautiful such finger like structures. So, this appears in a very regular manner, and we can measure, we can see that the wavelength, okay, of these fingers, the gap between these fingers, that is almost constant for any given set of film and then adhesive and the cover glass plate. So, here we have kept the adhesive film same, okay, but we have varied the cover plate. So, the cover plate becomes more and more stiffer here. Okay. So, the stiffer plates have been used. So, it is the least stiffer, then the stiffness increases over here, then increases further over here, and then increases here. So, very stiffer plates, when the we get a long such fingers, and some of the times the fingers break over here. Nevertheless, as long as this thickness remains constant and the modulus of course did not change, okay, did not change, the wavelength, okay, that remains constant for all these cases. So, actually what I want to say is that we basically wanted to understand that how in the case of the classical peel experiments with different tapes, okay, this kind of instability at the contact line appears. Okay, what is the origin of that? Is it because of the viscoelastic character, the viscous character of this adhesive, or because of its elastic character? So, what we find is that we have an adhesive film here where we do not have any viscous effect, we have only elastic effect, yet we see this kind of instability, and the wavelength of the instability remains independent, okay, of the rigidity of this top plate or the flexural flexible plate, okay, the stiffness of the flexible plate, it does not depend upon that. So, we call it flexural rigidity D, okay. So, it increases in the direction of the arrow. So, then we can find out, we can actually vary the thickness of these films, and we can also use different modulus of the film, okay. So, it so happens that this thickness, the wavelength, okay, of this instability that remains independent of all other parameters except the thickness of this film. So, as thickness increases, this wavelength lambda increases, and we can see the all data fall on a single master line, okay, with lambda is equal to 4h, this kind of dependence. So, this is a very generic kind of equation, relation that we get for this kind of incompressible, okay, elastic film in this kind of rectangular geometry, and this lambda remains independent both on the properties, material properties of the adhesive film, and also the flexural rigidity or the property of the flexible adherent from the top. So, we now understand, we now try to ask the question, what happens if we change the geometry? So, instead of having a rectangular spacer, we now have a glass sphere as the spacer, okay, and from the top we bring this flexible plate in contact. So, the flexible plate adherent that remains in contact everywhere except at this particular location, okay, where this glass sphere has been presented. Looks like a eye here, right, from the side view. So now in this region also where it is remain in contact, it happens something like this. The pictures here in front of you for thinner film, a 40 micron, here it is 80 micron, okay. Here this is the modulus of the film is 0.25 megapascal, shear modulus here is 2 megapascal. In all these cases the Poisson ratio is 0.5, remember that it is a incompressible film in all the cases. And what we find very interestingly, that this location, the film, this coaxially flexible plate remains in out of contact, or this film, okay, in this location and in this along this ring. So in this ring shaped region, okay, the flexible plate remains out of contact with this elastic film, and also out of contact along this on these bubbles like cavities that appear at the interface. Here for a thicker film, okay, it appears something like this, where this like say kind of a sun's corona, something like that. Here it appears like a, here the modulus increases, so here everywhere remains contact, okay. It is these locations where out of contact. So we see this kind of different kind of patterns for this experiment that we carried out. And what is interesting is that in all these cases we can find out an wavelength, okay, which is the distance between these cavities, and this wavelength, okay, actually remains as lambda is equal to 4h. It does not depend upon either the modulus or the flexural rigidity of the plate, it remains independent of that. So that is the beauty of this particular instability. It happens for all these cases, different elastic films that we tried with, for example 40 micron, 80 micron, all that, and modulus of the films also is there, and then the lambda however depends only on the thickness of this particular film. So we did the experiment in a somewhat in a different geometry, where we want to have this disc which is a disc which is a kind of indenter. So the indenter is in the form of a disc on this substrate, and so it we kind of apply a kind of torque over here. So this particular disc is placed on this particular film on this glass plate. So this is the glass backing, and then this is a rigid glass disc, this, so we can see through it, and this is the light source, and this is a microscope camera, and we put these different loads with di and do different these are this annular loads basically applied, right, annular loads, cylindrical weights that is applied, and this leads to this particular plate being bent to a very small, so bending is very small, but nevertheless it is there, okay, it is bent. And then what you do is that this glass disc remains bonded to this particular bigger disc, this we call it a rotating disc, and then this rotating disc very gently using this motorized drive is rotated. So what we are doing here, two things: one, we are applying this normal load from the top, okay, using this cylindrical weights, and over here using this drive we are also applying rotational shear over here, rotational shear, that is why, okay, shear over here. So that is why you say this is a rotational geometry. So basically there is both normal load and also this rotational shear load that is being done. Now why it is being done? Because we want to know that what will happen because if we apply also some kind of shear. So we can do in the rotational geometry we can apply easily the rotational shear load, okay, that is why we are doing this. And yeah, and basically we want to see that how this wavelength of this instability will change. First of all, whether the instability appears, and secondly is that what is the geometric aspect of this instability. Does it vary with this, will it change in this case, or will it the wavelength will change, etc. These are the questions, and these are there in my paper. You can have a look at it if you are interested, Langwood 2003 paper. So here when you just put the load and we do both the loading and unloading experiment. So we can continue to put one upon one after another. So this is loading and without shearing, okay. So with this loading and then we do unloading. So we can do both, okay, and we want to see that if there is any hysteresis in pattern formation. So if we load it, so the load increases, okay, and then we up to this point load increases. So, and after that it is unloading over here. So, this is the load actually decreases over here. So, you see that we start with a 0 load over here and we start with a, and we end with a 0 load over here. There is some difference in their surface structure, okay, that is there. Similarly, that this is another surface. 1 to H is loading. I see 1 to H. 1 to H was loading and Y to P is unloading. So, loading is up to this point and unloading is this point. Okay, so this is the kind of film that was used. Remember that this here the flexural rigidity is 1.2 Newton meter over here. So, that is because the film is bonded to a thicker glass plate over here. So, this has got a higher flexural rigidity than the films that I had used over here. Here I had mentioned actually this is 0.02 Newton meter, I should say here, flexural rigidity. So, we have varied the flexural rigidity also quite extensively. Now, when you apply shear now, these patterns transform into this kind of ring like structures. Okay. So, these rings are the locations where the film remains out of contact of the surface of this gas plate of this substrate. Okay. So, like that. So, what I mean to say is that there are this kind of instability pictures. So, this is this instability is isotropic. You can see there is no direction over here. Okay, there is no direction over here, and so this wavelength of this kind of instability can be obtained by what is known as the FFT. Okay, fast Fourier transform of this pattern, and that we did here, and we can obtain the wavelength from analyzing this FFT of these images. Similarly, FFT can be done over here also, and FFT appear as this kind of rings which are separated by some distance. So, we can here also we can obtain the frequency FFT, you know, it is the frequency domain. So, we can obtain the wavelength, okay, from this instability over here. So, in all the cases actually this varies with wavelength goes as about 4h. There are some dependence also on the load. So, I am not going to detail of that. You, if you are interested, you can look at it. So, we extended these ideas, okay, for this kind of viscoelastic films. So, in essence what we have is an adhesive in which the viscoelasticity has been controlled by cross-linking this polymeric material to different extent. Let us say that it is so in the actually how do we prepare this adhesive? We have a polymeric material on which put some kind of cross-linker. Cross-linker you have to put about 10% to cross-link it completely, but let us say we put it a very small amount, let us say 1% or let us say 1.5% or like that, and so they become viscoelastic to different extent, and then this film looks very much similar to the ones that has been used over here, okay, on this here, but only thing is that here it is completely cross-linked. So, I had used 10% cross-linker here, but for this viscoelastic films it is not 10%, it is just 1% or 1.5% over here. Otherwise, the experiment remains exactly same. So, we bring from top this flexible plate in contact, and then we spacer over here and let this contact line that to evolve, and this leads to different kinds of patterns once again, and here we can see these structures. So, here we have had it 1% and 38 micron, the film is about 38 micron, here it is about 38 micron, but 1.5% cross-linker. Here the thickness have been increased to 58 and then to 102 micron. So, as you can see in all these cases there are actually about two different types of fingers. One is this kind of like long fingers, and then these long fingers actually becomes unstable and they form this kind of smaller fingers. However, for this case 1% case, the fingers that appear are basically long, the side fingers have an angle with these long fingers. So, different other experiments people have seen such finger like structures. So, these are signature of viscous instability, okay, which is also known as Schaffman-Taylor instability. I am not going to go into that. Over here we have these fingers which appear normal to this main axis. So, see, this is the main axis of the finger, and these side fingers they appear normal to the axis, and then we can measure the wavelength of these fingers, okay, wavelength distance between these fingers, and over the whole image, and we can obtain the wavelength. And surprisingly, here also the wavelength data, these green symbols that fall on the data that we have presented earlier. So, that means lambda here also goes as 4 into h. So, what it means is that in this case also the wavelength, okay, these short fingers, side fingers that appear, they represent this elastic instability that we have saw with the elastic films, although these long fingers are signature of the viscous instability. So, both the kind of instabilities are present and both the kind of structures are there. So, basically this is what I wanted to talk to about this kind of instabilities and their origin and how they affect the peel force and all that I have not gone into. I am not going into right now, and there are lots of papers on the viscoelastic adhesive peeling, and if you are interested you can go through that, but the basic idea of peel force and how to obtain the fracture energy, that I have talked to you about. So, there is one more point that needs to be said, is that whether do you see the instability everywhere? No, not all parameters. So, there is a critical thickness that is there. So, this critical thickness is given by this Hc. If the film thickness is smaller than this line, the critical thickness, the instability appears, otherwise not. So, in this case, the critical thickness actually scale as this particular quantity. So, d is the flexural rigidity of the plate. It is given as, in the its unit is Newton meter, and the mu is Newton per meter square. So, this is the modulus of the elastic film. So, the ratio of that is meter cube and to the power 1 by 3, so it is meter. So, d by mu, okay, that defines length scale. So, that defines the critical length scale, critical dimension. Okay. So, the thickness of the film, if it is smaller than this critical thickness, okay, then only instability appears. For the larger case does not appear. So, that is another point. So, that is to be noted. So, these are the things that we keep in mind when you do this kind of peel experiments to find out the fracture energy of an adhesive with respect to a substrate. There is another point, is that how does this contact line look like? So, we actually carried out this kind of AFM scanning of the surface. So, for that we needed to freeze or this pattern, because these are elastic pattern, elastic instability pattern. So, elastic instability means the moment the top plate is removed, the instability goes, but we there's some way we made this freeze this or cross linked these patterns when the instability was present. These are those finger like structures, and then we did the AFM to find out how does this the contact line they look like. So, these are the kinds of pictures for the AFM. So, at these points, okay, the picture look like this. There is a sharp decrease, okay, in the sharp fall in the film surface, okay, at this point. So, this portion is in contact, this portion is not in contact. So, at this location the AFM picture looks something like this. So, there is a sharp fall in the thickness, or the gap sharply increases between the top plate and this surface. Remember that this is something like this, this is something like this actually, and this is the cover plate, this is the film. So, we are looking at very close to this surface, the instability appears something like that. So, we are seeing over there, and this picture is taken, okay, at a different point. So, this picture is over here, and this picture in essence at this particular point. So, there are two different points at which this picture is taken, and this shows that how this pattern, okay, the film surface, the film and the top plate distance gap that increases over distance, okay, that is what it shows. We can do the same thing by looking at the interference patterns. So, here monochromatic light is used under optical microscope. This is a mercury vapor lamp, okay, to show that how the so that this is basically the fingers, and the fringes appear. So, this at the gaps, okay, how does the gap vary between this cover plate and the film at the very close to the top tip of this finger. That is all the picture speaks about, and there is a flexible, So, these fringes, the gap between these fringes, okay, can be obtained by looking at the wavelength of this particular light and the fringe patterns. So, the distance between the fringes is basically lambda by corresponds to lambda by 2, a gap lambda by 2, like that. So, from that one can actually obtain the gap between this gap S between the cover plate, flexible plate and this elastic film. One can do all that. So, in a sense, basically wanted to show you that in experiments, okay, how to investigate critically, okay, this kind of like adhesive problem. I will now shift gear and I will like to focus on the bending of a thin sheet. Why bending is important? Because as you can see here in this experiment also, that we have this flexible adherent which we try to lift it from this elastic adhesive that remains bonded to a substrate, let us say, and then there is a bending of this plate, okay, that is there. So, in the case of most square knot tapes, adhesive tapes, we have got a very flexible, very soft backing. So, we do not much worry about the bending energy that is stored in this or the stretching energy that is stored in this film, but that is not correct because if you want to do rigorous analysis, then this bending energy needs to be considered, and particularly if this adherent, okay, becomes not so soft but stiffer, then the bending energy, okay, further increases. So, therefore, we need to worry about, consider about this bending aspect, and that will also give us this idea about the flexural rigidity. So, today I will stop here and I will take up this bending aspect in my next lecture. Thank you.